So, Mr. Bakker, why did you decide to research semiconductors and diodes in graduate school?
That's a big question. Because I wanted to do something that was good. So when I graduated from undergraduate school back in the Reagan era, a lot of my friends were getting good jobs and going on to do research in funding associated with the military. So I didn't want to end up at the end of my life making weapons. So when I decided to go back to graduate school, before I looked at programs, I thought, what do I want to do? And I got it. One of my picks was doing solar energy, doing research on improving efficiencies of solar cells and studying applied physics in solar energy.
Do you think that your father's work influenced your decision to major in physics or your decision to pursue these research interests?
My dad was a great influence on my life, and we would sit out in the yard and talk physics about how things fell, or go out at night and look up at the sky on my side yard and talk about physics. We were always talking about physics. I think from the time I was born, I thought I was going to major in physics. I didn't want to go into semiconductor physics, but like I said before, it was when I picked what I wanted to do, it was really more on what's going to be worth doing. And I had grown up by that point to think, any field that you get into has richness and depth, and but not all fields really have the same value at the same time.
So, could you briefly describe what a semiconductor is and what it does, maybe why it's important?
Semiconductors in of themselves aren't that interesting. It's the fact that we can do interesting things with them. So like silicon or germanium or others, you can add impurities to them. Impurities can affect the energy levels of free electrons, and then when you join them together to other semiconductors, can create potential barriers that allow current to do interesting things like flow one way or not the other, or to be able to be turned on and off by an electric field. So semiconductors, one of the great things you can do that you can't do with an insulator or a conductor is I could apply an electric field and make it go from being a conductor to an insulator. And therefore I can turn on and off current with an applied signal. The ability to create a switch, pretty important. Pre-semiconductors had vacuum tubes.
Mm-hmm.
High energy, big, slow. So, and the goal, even from that time, we knew you needed a junction, a device that could be in a combination of states. So semiconductors, at first they weren't, they were pretty big. They had some really big clunky ones. Schottky in his first transistor was fairly a large device, but they're able to be made smaller and smaller and smaller, use less power, and be made from some pretty cheap materials like silicon. So that was the big advance, is use less power, smaller, break down less.
Could we transition to talking about integration and the idea of integrated circuits?
You can make a circuit one component at a time, and then you plug it into some kind of board, solder it together. So manufacturing processes of non-integrated circuits are going to limit how small they can get. When vacuum tubes would fail in a large computer circuit, you'd go in and you'd replace that vacuum tube, that single switch. Semiconductor transistors and diodes are going to be more reliable. They can be made smaller, and once they get so small, you aren't going to be able to make them in a integrated form. Like when I was your age, my dad brought home a poster of the first chip. It was the first one to have 1 million transistors on it. But they did it all with photographic techniques that they would take, just like microfilm. Somebody would write a circuit on a large, like out here on this table. And I'd say, I really want it to be like 1 million times smaller because I've got all this circuit. And so then they'd take a picture of it, and with a series of lenses, they'd make it smaller and smaller, and then they'd shine it on here. But just like photographic film can be optically sensitive, the stuff they'd shine it on would be optically sensitive. They'd develop it, and then they'd put it in an acid bath and etch away the parts that they didn't want. So you might have a thin layer of conductive stuff, or the different layers of stuff, and you could photographically etch away different layers to create this circuit.
As a physicist, computer scientist, and fervid learner, you have a wealth of experience in multiple different fields. Can you please describe the interdisciplinary nature of your research and teaching?
These days, there are so many things that can't be solved analytically that some level of programming is necessary for all computers, physicists too. So there's this need. People are hungering. People want somebody who can do some programming to solve the physics problems they want to solve. I came to Deerfield. I was teaching physics for about 10 years before a bunch of students wanted to start taking computer science. We didn't have any computer science program at that time. And so they got me, they were looking around, so I said I'd teach it. And I taught that for about 3-4 years. As it grows, I just try to think, well, what would be a cool course to offer? And often it's things I'm interested in, and I get to learn alongside the students things I'm interested in. So
that kind of organic growth sounds really cool.
Yeah.
So looking to the future, the technology behind semiconductors hasn't really changed in the past 50 years. As Moore's law is slowing down, what do you think the next big breakthrough in computer hardware will be?
There are in these computer systems, you're looking at, like I said, the same problems persist. You want to make things smaller, you want to make them faster, you want to make them cheaper, but really you don't necessarily want to do just that. You want to put them in systems that solve problems. So on top of that, you have your layers of software. And I think we're going to continue to make advances on all those areas. I think fundamental change, where is it going to come? Quantum computing, I think that'll solve a small set of problems and begin to become more applicable. I don't think it's going to replace the stored program computer soon. That's our main computer. It's a little bit like what's going to happen with energy. We're going to have a broad mix of things solving specific problems. And people are working at every level of this. It's fascinating. Whether you're making a transistor, whether the purity of your doping materials, the cost, the manufacturing processes, people will continue to make improvements, but I think they're going to be harder to come by. But I do think we're seeing a broadening out of solutions for specific problems.
That's about it for our questions. Thank you, Mr. Bakker.
You're welcome.